Hello, everyone, and welcome to another live session of the online course, the first of 2016. Looking forward to your questions.
So let's go ahead and get this out of the way at the beginning. Can you talk a little bit about some of the new astronomy discoveries that have been announced this week? The first of which is, or the sort of most exciting of which is new potential planet 9. Right.
So people have been, as we know, on a roller coaster over this. There was the demotion of Pluto, which actually happened many years ago now, and some people have still not got over that. Alongside that, there have been a series of surveys underway, especially by the group, the CALTECH group that announced this recent discovery, to try and find large objects in the Kuiper Belt. So that is in the zone of 40 to 80 astronomical units, beyond the orbits of Uranus and Neptune, looking for objects that are Pluto-sized or larger. One object that's larger than Pluto has already been identified. There are another 3 that are very close to Pluto in size, and actually it's very uncertain to measure sizes that far away, so you already could have several objects larger than Pluto, and their expectations have always been, right from the start of these surveys, Mike Brown was one of the leaders of these at Caltech, that there would be 6 to 8 objects larger than Pluto in these large volumes of space beyond the traditional edge of the solar system. And so what we've been hearing this week is the inference, the strong inference, that there is a large object nearly Earth-size, so substantially larger than Pluto, in the depths of the Kuiper Belt. It's an indirect indication because the object hasn't yet been discovered, and it's because any object that far out perturbs objects that are closer in gravitationally, and so the signature that's been seen is the clear signature of a large object moving in that outer zone. The perturbations extend over a large region by the inverse square law of gravity, and so the fact of these perturbations indicates a massive object, but doesn't really pin down exactly where it is and what its orbital speed might be. So they've not yet identified it, but basically they're pretty confident that that'll happen eventually.
All right, the next question is actually quite general. Can you talk about what the difference is between theory, fact, and truth?
Right, very good question, of course. I mean, in any science class or consideration, that's right at the ground level of the subject. How do we distinguish between things that are true and not true, and what is the role of theory? And astronomy is particularly interesting in that regard, in terms of what we're talking about as epistemology, the theory of science and how it works. So let me just mention that right out the gate, that astronomy is unusual because it's not a lab science. If you are a physicist or a chemist or even a geologist, the objects of your study are available to you. They're available and they can be brought into controlled environments in the laboratory. Physics works entirely that way. Chemistry works that way, and biology too. So most of the sciences work in terms of direct experimentation. And so you can form a hypothesis and test a theory and control your experiment in the lab. Astronomy is not that way. The objects of study are remote from us, and all we have is the information typically of electromagnetic radiation. And we don't have as much information as we might want because objects are faint and far away, and we don't have control over that information. It's just what we can gather with our telescopes. So the basis for distinguishing, fact from fiction, or something that's true and not true in astronomy, is a slightly longer and more convoluted process, because you don't have a lab experiment where you can test a hypothesis, yes or no, end of story. In astronomy, the information tends to be a little more ambiguous. So to take a simple example, proving the existence of black holes, stellar mass black holes, and the hypothesized, of course, a century ago. And the evidence that black holes actually exist in the universe took several decades to come, and it was really probably only through the 60s and 70s, by the mid-80s, that most scientists decided that the evidence of binary systems of stars where one companion was more massive and it was a remnant, so it had to be a black hole theoretically, was good enough that we could all say black holes exist. It didn't happen overnight. It didn't happen with a single observation. So in astronomy, the science is a little more tentative than in most sciences, in other brands of science. That doesn't mean that we don't know things. That doesn't mean we aren't sure of things. And the closer we are to the Earth, the more sure we are of them. starting with the Earth. As you probably know, the Earth's age is now measured with a precision of the second decimal place in the billions of years, so very accurate determination. And so some measurements in the solar system are based on direct observation with spacecraft and probes and even samples brought back. And that makes it much more like a lab science. But beyond the solar system, which is most of the universe, our information is indirect. And so we have to make models or theories of how the objects that we're working with behave, which are based on physics. The underlying science of astronomy is physics. So we have theories based in physics of how stars work, of how massive or regular mass black holes might operate, of how the universe expands or behaves at different points in its history. And those theories are tested by observation. But it's a continual process, and it's a process that doesn't move forward steadily or at a particular speed. It sometimes depends on innovations in our observation, opening up a new wavelength regime, or developing a new type of precise detector to put at the back of a telescope. It's still the case. This tentativeness doesn't mean that there are things we don't know, and it doesn't mean that the science doesn't move forward. But it just means that astronomers are more likely than other scientists to say, rightly, we're not sure, or we don't quite know what's going on here. The number of things we're absolutely sure of is actually quite modest.
All right, the next question is from Mike, who is on live with us now. We have seen stars of many sizes with our telescopes. Is there a theoretical limit to how large a star can get?
Yes, there is. It's a good question. We do think we have a pretty good generalized theory of stars and how they work and how they form and how they live their lives. That theory was developed by Hertzsprung and Russell in the 1930s, and the theory behind it by Arthur Eddington, also in that same time frame. And it's a pretty mature theory, almost 100 years old. That theory describes the structure of stars. And so if you just imagine a certain amount of gas that's collapsed by gravity to form what we call a self-gravitating object, is an object that's sustained at a particular size by the amount of mass and therefore gravity it has, and the countervailing force is the pressure from fusion reactions in the core, if it's a main sequence or other fusion operating star. And those simple equations that balance radiation pressure against gravity tell you how big the star is. And so those same equations can tell you how big the biggest star is. The biggest stars, not surprisingly, are the most massive stars. They're stars that they're typically blue or red supergiant stars. Antares is an example of a red supergiant star. There are other examples that are visible in the naked eye sky. And these stars, which have masses of perhaps 20, 30, maybe 40 times the mass of the sun, are thousands of times, even tens of thousands of times larger than the sun being about 1 million kilometers in diameter. So stellar structure and stellar theory does tell us that some stars are extremely big and what their size is. Now, it's important that these sizes are inferred from the theory. They're not measured directly. It's very difficult to measure the size of stars because these stars are of order millions of kilometers across, and they're tens or hundreds of trillions of kilometers away. So they subtend tiny angles in the sky. And then to answer the question directly of the maximum size, that essentially correlates with the maximum mass of a star. So by the time you go above about 100 times the mass of the sun, even in theory or in a computer, if you simulate it, if you try and form a stable object, it doesn't happen. Because the gas that's collapsing, 100 solar masses worth of gas free falling by gravity and collapsing, it collapses so violently that it bounces essentially and blows itself apart before it can form a stable object. And so that process, that limit based on the stability of a large gas mass collapsing by gravity, means there's also an upper limit on the size of any star.
All right, this question is the cosmic microwave background evolving in time, or is it constant? Will it disappear one day for future observers? And that's coming from a live question.
Yeah, the microwave background is evolving because the universe is evolving. So the microwave background, to rewind a little, is the relic radiation left over from the Big Bang. So the Big Bang is the creation event, the origin of the universe 13.8 billion years ago, a situation of extreme heat and high density. And as the universe expands, the radiation that filled the infant universe has expanded and cooled, just as if you had a bathtub of cold water and you poured some boiling water from a kettle into it, that boiling water would spread out and expand. So say that boiling water was colored with a dye, you would see it spread out and expand, and if you measured the temperature of the colored water, it would rapidly cool. Well, the universe is doing the same thing. As the universe expands, it cools, and that means radiation in it is cooling too. The process is actually the redshift, so it's the expansion of space-time itself, which stretches the wavelength of the photons, and so takes them to lower energies. At the present time, 13.8 billion years after the Big Bang, that radiation has a temperature of 2.726 Kelvin, just a little above absolute zero, and it radiates mostly in microwaves, invisible small wavelengths. And that process will continue. So in the future, as the universe continues to expand, actually, and at an accelerating rate due to dark energy, that radiation's wavelength will continue to be stretched, the radiation will continue to cool, and will continue to lower in energy down to pure radio waves rather than microwaves. And you can predict how that process will go. It's very simple, actually. As the scale of the universe doubles, so the wavelength of the Big Bang radiation doubles, becomes twice as long. And so we can take the Big Bang expanding universe model and predict very simply, the math is even quite simple, what the wavelength of that radiation will be in the far future. And there's no end to that, as we believe the universe will continue to expand forever due to dark energy. The radiation within it will continue to cool until it becomes incredibly long wavelength radio waves of hundreds or thousands of meters. I mean, radio waves that are longer than anything we can observe on the Earth. And that radiation will, of course, gradually cool asymptotically, never quite reaching zero, but cooling towards absolute coldness.
All right, the next question is from someone, again, who is on with us live. What is the intent behind sending humans to Mars? I suppose it's much easier and more efficient to research most of the planet with robots. So why send people?
Right. It's a big argument in the space science and astronomy community whether we should send people to Mars at all, because as everyone knows, sending people in space is expensive and difficult. Very expensive. I mean, for the price of a manned Mars mission, which is very hard to estimate, but because it's a staged approach. You don't just send a single spacecraft. You actually have to send a couple of spacecrafts to leave supplies, to give them a place to stay. You have to probably have a rescue mission available waiting in the wings, because NASA has essentially a zero risk tolerance. So it's very expensive, and the numbers I read go from 50 to 150, maybe even $200 billion, extremely expensive. And whatever the price tag is, it's incredibly high. For reference, NASA's budget is about $18.5 billion this current fiscal year. So why would you even do that, given how expensive it is? And I think there's only two answers at the moment. The first answer is that robots are not there yet. The servicing of the Hubble Space Telescope by astronauts was an object lesson in the fact that at the moment, our technology is not good enough for robots to do all the complicated things we might want to do in space. Essentially, the NASA administrator looked at a robotic servicing mission for the Hubble Space Telescope, its last servicing mission, and looked hard, and he was an engineer, so he knew how to judge this, at a robotic servicing mission instead of risking astronauts' lives because 2 shuttles had already been lost. And he concluded as an engineer, and a set of engineers looked at this pretty hard, that servicing the Space Telescope, replacing instruments and power panels and solar cells and all that was just too difficult and complicated to do with robots. A Mars landing and sampling the soil and doing various experiments is also quite difficult. Now, obviously, we've done things with rovers, but there's a level of complexity and subtlety of study and scientific decision making that humans can do that robots just can't do yet. And I say yet because really, with the rate of progress of technology and artificial intelligence that could be embedded in machines, you're really only a decade away from machines that probably could rival humans in a remote location. And since we're talking about a Mars landing that's a decade away anyway, I guess you see the logic that probably you should just wait and do it with robots, and it'll be much cheaper. Well, if that was the only argument, then I think the argument is clear. The second argument, of course, is that we want to be there. We want to be doing it. So there's a part of the general public, and there's a part within NASA and the space science community that wants us to be pushing this frontier of exploration, just as people did when they first went to Antarctica, or they first moved across the parts of the planet that had never been inhabited. It's a sense of adventure. It's a sense that we are doing the exploring. And so there's a segment of the community, and there's a sense that public opinion would rally much more strongly, even at great expense, behind a manned mission to Mars as opposed to a robotic mission to Mars. And if you doubt that, you just have to imagine The Martian, the movie and the book, and imagine that it would not quite have had the emotional resonance it did if it was just about a cute little robot doing things on Mars.
Right, the next question is from Aurora via email, and she asks, how immediate are the threat of asteroids?
Asteroid threats are inevitable, is the way I'd put it, but not immediate. They're not immediate in the sense that it's a clear and present danger right now as we speak. But the density of debris in space is such, and the known history of impacts on the Earth is such that it's certain that there will eventually be a large impact. Maybe not a civilization, or maybe not an Earth-destroying, biosphere-destroying impact, but a continent-destroying, truly catastrophic event, a kilometer-type size impact happening at tens of thousands of miles an hour, enormous amount of energy. So it's a danger because we know it happens, and it happens randomly. All you can do from the inventory of near-Earth asteroids and space debris is predict the average time between impacts. And that is an average, but the incidence is random. So you have no predictability about when the next event will occur. And so we might say, well, the dinosaurs and other species were destroyed by an impact 65 million years ago, and the average frequency of impactors of that size is once every 100 million years. And you can do the simple math and say, do the subtraction and say, well, we got 35 million years, we're fine, don't worry about it, because that impact could happen essentially any time. But in any given period of time, like a year or a decade or a human life, the probability of it happening is very low. So what scientists try and do is guard against that low probability, because it's one of those awkward things. It's a very low probability event that has enormous consequence, so you have to take it seriously. And the strategy that space scientists use, of course, is to be vigilant, which means survey the sky for all the near-Earth objects, that is the objects that could cross the Earth's orbit potentially, and make sure you have an inventory of them, especially those that are bigger than a few hundred meters, which are the ones that really cause huge damage. And NASA's was tasked by US Congress actually to do this over a decade ago, and is about 90% through the job. That's not going to reassure people, because that 10% that they haven't cataloged yet could still be the one that causes the problem. But that's going to be done in a year or so. And with that inventory and a monitoring network to see whether any of them actually will come close to the Earth, it pretty much means that we don't need to actively worry about this possibility.
Okay, the next question is from Divyesh, who is on with us live. And the question is, I'm struggling to understand the concept that the universe is flat. We can see galaxies in every direction around us. Surely the universe must be anything but flat.
Well, it's a matter of direct observation, in fact, that the universe is flat. Measuring the curvature of space-time is not a trivial thing to do. The fact that space-time could have a curvature, of course, only emerges from the theory of general relativity. In all of astronomy until Einstein, nobody even questioned that the universe was not flat, because to Newton, and within Newtonian gravity, time and space are smooth and linear. And so Newton never contemplated a space-time curvature, or the fact that space itself was curved, or that light would travel on curved paths through space. All of that is put into play by general relativity. So now the question has to be answered. When you have a gravity theory that says that the curvature of space-time is coupled mathematically to the density of mass and energy in that region of space, or globally for the whole universe, you can go out and measure it. Those are interesting and difficult measurements. The most precise measurement of space curvature actually uses the microwave radiation left over from the Big Bang. Remember, when we look at the microwave sky, we're seeing a snapshot of the universe 400,000 years after the Big Bang, at the time stable atoms formed and radiation was able to travel freely through the universe. We can compare how the speckles, if you like, or the small fluctuations in temperature of the microwave background would change as they travel through space for 13.8 billion years. And if the universe had a curvature, the size of those speckles would either be magnified if the universe had positive space curvature, or demagnified if it had negative space curvature. And in fact, when we compare to a model, the speckles are not magnified or demagnified, which indicates flat space-time. That means essentially that light is traveling in perfectly straight lines through the universe as the universe evolves. That's actually quite a precise measurement. The universe is flat to within, I think now, less than 1%. So if there's any space curvature on a cosmic scale, it's extremely subtle and slight. So that's a matter of observation now. We've actually confirmed that that is the case.
All right, the next question is from Ian, who is on with us live. Hello, I was wondering, what is the farthest thing from us we now know of, and how far is it from us?
So the furthest thing or object, the furthest evidence, if you like, or signature of the universe is pretty much the microwave background radiation that I've alluded to, the relic radiation of the Big Bang, because we see that that's a signature of the universe 400,000 years after the Big Bang. And 400,000 years as a fraction of 13.8 billion years is a tiny fraction. So that's essentially looking back 99.99% of the way towards the Big Bang, or the time towards the Big Bang. The furthest object is not that far away or that far back in time, but it's getting pretty close. So there's a pretty active and competitive research field involved in trying to find the most distant galaxy in the universe. And to an astronomer, the measurement is actually a redshift. So you measure the redshift, the amount by which the radiation is shifted or stretched due to the expansion of the universe relative to something that would be in the lab. And that converts through the model, the cosmology model, into a distance. At the moment, so there's argument about this because there's always a sort of research froth of things found in the Hubble Deep Field or very deep surveys where people are struggling with not many photons to work with to show the redshift and the distance. But the typical most distant galaxies are at look-back times, that is, how long ago are you looking back in time to when the light was emitted, that are about 12 billion years, 12 to 13 billion years. It gets argumentative around 13 billion years, but there are secure examples of about 12.8 billion years. So that's about 1 billion years after the Big Bang. So that's within the first 10% of the age of the universe. If you want to go to things that are not confirmed, that are in the research literature, but not everyone believes them yet, then there are hints of objects within 500 million years of the Big Bang. So going back to 13.3 billion years ago. So that's the time. The distance is a little more interesting because the universe was expanding faster than light for the early third of its expansion. And so the distance to the oldest object we've seen is actually a distance more like 35 or 38 billion light years. Interesting, in a 13.8 billion year old universe, that light could have traveled that far, and it's because the universe was expanding faster than light.
So our next question is from Steve through an email. What is going on with regards to light pollution? What is the role of the IDA, the International Dark Skies Association, and are they able to really make a difference?
Yeah, it's an important question. Astronomers worry about this a lot, and a lot of the general public care about this too, because they, maybe not in their daily lives, because most people live in cities and suburbs where they just accept that there's not much of a night sky to look at. But when they go out on holiday or go to a remote location, they want to enjoy the night sky. So the big picture here is that it's not going in a good direction, because as civilization grows, as mega cities around the world grow, there are now 10 cities, I think, with more than 10 million people in them. Most, of course, are not in the United States. These are just glowing like crazy, and you could not really do serious astronomy within 100 miles of a place like that. Also, the fraction of the population that lives in rural situations is diminishing. So it is leading to an interesting situation where the parts that are urban and suburban are essentially impossible for astronomy, but some of the rural areas, partly for reasons of economic decline, are actually getting a little darker. But overall, because the population of the world is growing and because low industrialized countries are growing and getting industrialized and developing more lights and more commercial lighting, the light pollution problem is getting worse. Well, astronomers don't need or care if the universe or if the entire world is getting brighter, as long as they have dark places to do their observing. So astronomers are, not fixated on trying to reverse light pollution around the world, just in trying to preserve the sanctuaries where the light pollution is modest and stop it from growing. And there's reasonable success. Pima County, where I live, in the University of Arizona, home to a set of mountaintop observatories, has the strictest lighting ordinances in the country, also shared with San Diego County, where Palomar Observatory is, but it's kind of too late there because San Diego and LA have almost bled together as urban conurbations, and Palomar's between them. But our lighting regulations for low pressure sodium and reflection of commercial lighting downwards so that it doesn't shine up into the sky has sort of put a lid on the rate of light pollution getting worse. The other major observatories where this is an issue are in a slightly better situation. The Hawaiian observatories are on the Big Island, and the Big Island economy has never done very well, actually, over the last few decades. So the light pollution has been growing at a modest level, and the observatories bring a lot of economic benefit to the Big Island, and so they're pretty motivated on the Big Island to not have light pollution get out of hand. The other major place where observatories are is Chile, and Chilean observatories are in truly remote regions, and the Chilean government is strongly supportive of not compromising the observatories. Because they're so far from population, the big threat to Chilean observatories is actually from mining operations, because it's very mineral rich, and a mining operation, is usually floodlit, working 24 hours a day, and a pretty horrible thing to have near an observatory. And that hasn't happened yet. So astronomers are, mildly optimistic that the darkness of their special preserves, their best places, will be retained even as the world overall gets brighter and brighter.
Okay, our next is a live question from Anna. She asks, I still can't make up my mind if I believe in UFOs or not, and in other creatures having contact with our past cultures. If you believe in life on other planets, why don't you believe in UFOs?
So it's a logical question, and it's one that astronomers have to wrestle with. The dichotomy here, or the conundrum, is that with the evidence for Earth-like planets from Kepler, we have projections, essentially, of roughly 100 million truly Earth-like habitable planets in the Milky Way. That's a huge number. That's a reliable number based on extrapolation of Kepler's work in the more nearby universe. So if you have 100 million truly Earth-like places where life could have evolved, and you have a lot of time for that to happen, it's almost illogical to imagine that we're alone in some sense. And so if we're not alone, and there's certainly time for civilizations to have got to our level or better, then you're left with a question of where are they? And that was the question Enrico Fermi asked famously in 1950. And so given that backdrop, it's not irrational or illogical or wide-eyed speculation to say, well, UFOs, maybe we could be visited, and maybe we have been visited. And that's up to that point, I think everyone's on the same page. Scientists will admit that it's not an irrational question, and the people who are asking that question are well motivated. The next part is the tricky part. That's where people part company, basically, into two different groups. And it's the bar. Where's the bar set for demonstrating that we have been contacted, or that UFOs do represent alien visitations? And most astronomers, my cohort, go back to Carl Sagan, who famously said, extraordinary claims require extraordinary evidence. Clearly, if you are hypothesizing contact with an alien intelligence that rivals our own, that's an extraordinary claim to make, an extraordinary situation. It's a transforming situation for world culture, if that were the case. And so, rightly, the bar is set very high on the evidence to support that claim. And astronomers, some astronomers, I admit, are just simply not interested or willing to deal with it. They just get exasperated by UFO claims, and they just say, I don't have time for that. I got to do my research, or I want to talk about things we do know, not about that. I mean, I give it time because I think it's worthy of time, but it doesn't mean I delve into every UFO sighting and scrutinize the evidence. I don't have enough time to do that. The simple fact is that given the high stakes of the claim of UFO visitations or abductions, I mean, you can take it up the whole spectrum of UFOlogy, the evidence is completely unconvincing. It is totally unconvincing, by which I mean anecdotal evidence doesn't cut it. You know, people say things, and it's not to say that they're being fraudulent or lying or trying to mislead. People are, you know, the legal system is wrought with the idea that eyewitnesses are probably the worst people. You would never want to convict someone of murder or send them to death row based on eyewitness testimony, riddled with errors and perception biases and misjudgments and so on. So eyewitnesses are notoriously unreliable. So you could not use them to adjudicate such an important question alone. They could corroborate. Photographs or images, that now in the digital age, I mean, even before the digital age, it was very easy to fake photos. And now it's so trivially easy that astronomers just completely dismiss digital imagery as supporting evidence. This picture in the sky, this cigar-shaped object, whatever. It's just too easy to fake it. It's not good evidence at all. And so the high bar is set with physical evidence. If you had a physical evidence, an artifact, a piece of metal, an unexplained, you know, even a signal, electromagnetic signal, something you could capture with a telescope and share with other people. The bar of science is set with corroborated evidence that others can independently judge and inspect, and that is usually most easily done with physical evidence. And there has never been physical evidence. And just retreating to a conspiracy theory that says the physical evidence is hidden by the government on Area 41 or whatever, that's just a convenient, that's a cop-out essentially. So, and now I will betray my exasperation, because some people who want to believe this stuff will sort of retreat into the most strange and convoluted logical arguments to support their claim, when in fact all astronomers are ever saying is, give us your evidence, and it better be good, because you're making a pretty extraordinary claim. So that's why the community of astronomers has not bought into the existence of UFOs as a fact.
Okay, our next question is an email question from Lucas. He says, hi, my question is relating to the fact that the planet travels faster when traveling towards the sun, since it always covers the same amount of area in the same amount of time, which would suggest that the Earth accelerates. Does it accelerate? If it does, why don't we feel the impact?
Right, it's a good question. It's Kepler's law, which is a reflection of Newton's law of gravity, the inverse square law of gravity, showing that the force increases with the inverse square of the distance. That maps into changing speed in an elliptical orbit, which is the most generalized form of an orbit, such that when the planet is closer to the sun, or the moon is closer to the planet, if it's a moon orbiting a planet, it moves faster, and Kepler's law describes how that speed changes. And the Earth is doing that, but the Earth is in only a very slightly elliptical orbit. So the extreme elliptical orbits that are familiar to us in the solar system are comets, because comets spend most of their time in the deep freeze, far beyond the Kuiper belt at distances of thousands, tens of thousands, even hundreds of thousands of astronomical units, where they're barely moving and very far from the sun, and so dark and almost invisible to a telescope. And then when they move into the inner solar system, they speed up according to Kepler's laws, and they whiz through the inner solar system, heat up because of the sun and develop a tail, and then go out where they spend almost their entire orbit moving slowly far from the sun. Well, the Earth is just doing a very mild variation of that. The Earth is only 4% deviated from a circle. It's only elliptical by 4%. And if you were staring at a circle that was squashed by 4%, you actually would have a hard job perceiving that with your eye. In other words, it's a very subtle variation. And so the speed variation is similar. It's of a similar order. It's a few percent. And that speed variation in our orbit, especially, you know, given that it's a smooth variation, varying very slightly from one day to the next, is why it's completely imperceptible. But it is measurable. And so we can bounce radar signals off other astronomical objects and very clearly measure the Earth's acceleration or variation of the speed in its orbit.
right, the next question is also from email. It's from Jean-Marc. My question is about gravity. I understand that gravity is due to the curvature of space-time at large scale. I can understand that, but right at the Earth's surface, that's not clear to me. For instance, why doesn't light fall down as an apple does?
So it is applying at the Earth's surface, but the Earth is a very mild situation of gravity. So the formalism of general relativity, which relates mass energy density to space-time curvature, applies in all situations. But when the mass, and especially the density of mass, because remember, it's the sort of concentration of the mass that really counts. When the mass is low and the concentration of mass, or the density is low, which is the case of the Earth, just a big rock, this effect in general relativity is extremely subtle. It's extremely small. And so these effects are happening, but they're happening at a level of 1 part in a trillion or less. So at the Earth's surface, if you were to look for the deviations implied by general relativity caused by the Earth's gravity, and there'd be a set of phenomena you'd be looking for. You could look for the deflection of light caused by that mass. You could look for gravitational redshift, that is sending a light beam out from the surface of the Earth. It actually has to struggle against the Earth's gravity, and that light beam should be reddened slightly, the gravitational redshift. You could look for the speed of clocks, the clocks running slightly slower in the stronger gravity. All of those effects are predicted by general relativity, all are real, and they've actually all been measured, but they're all at a level of 1 part in 10 to the 13, or like a part in a trillion or less. And so it's fascinating because the effects are real, they're completely imperceptible to everyday life, and they require the most extraordinary precise measurements. Actually, the first of these measurements that was done was the one that involved time. Back in the 1950s, when the first molecular clocks, so these are atomic clocks that actually use molecular oscillations. So the very first accurate timekeeping pieces we had in our civilization in the 1950s, back in the time of the Cold War, pretty much, they took 2 molecular clocks accurate to 1 part in 10 trillion or whatever, and they flew one in a U-2 spy plane up at a very high altitude, and they left the other one on the surface of the Earth. And the one that was flying around in a U-2 plane for 24 or 48 hours, when brought back into the lab, had been running very slightly faster than the one that was left in the lab, demonstrating that time depended on the local gravity. So that was an extraordinary experiment at the time, 50 years ago, to confirm general relativity. But again, nothing you would see with your iPhone or your watch, as these are tiny, tiny effects because the Earth's gravity is kind of modest.
All right, the next question is a live question. What is the political impact on space exploration nowadays? Is there still a space race going on for colonization? Is bigger cooperation between superpowers desirable for the sake of exploring space faster, and are there territorial concerns?
Yeah, it's a great question. A lot of parts to it, and they're all in play, and they're all important right now. So yes, there is a fairly competitive space race going on. There's sort of 2 things going on. One is the privatization of space, which we've witnessed pretty much weekly in test flights. Elon Musk seems to alternate between a stunning success and a catastrophe. His most recent was a disaster, but he had a success before that. And Jeff Bezos had a success. So the private space program to get into Earth orbit without using government money, that's doing very well. On the larger geopolitical landscape, there is both cooperation and competition. The cooperation is the cooperation that's been happening for decades with the United States, Europe, and Japan. Japan is a significant space power. Europe, obviously, operating as one entity with 350 million people and a large combined budget, is also a big space player. And the US and Europe and Japan have been cooperating on space missions, on astronaut training, on all sorts of things, for 50 years. That's a very stable and healthy relationship. The rivalry part, or the competition part, is also interesting, because it's no longer now a competition with the Soviet Union. Russia is in, it's pretty much a second world country now and heading in the wrong direction, especially as the oil price goes down. Their economy is fantastically dependent on oil. So Russia just simply can't afford to spend much money on the space program. They're still limping along on slightly modified versions of the Proton rocket that they used in the 1960s, contemporaneous with the Saturn V. And indeed, they can make the Proton rocket and the Soyuz go up to the space station, so they can get astronauts into orbit fairly reliably, but they're not innovating. They're not developing new capabilities. So the Russians are sort of also rans now. The big player that's new and recently doing very important stuff is China. China's been increasing the size of their space program at a rate that their economy's been growing until they recently plateaued. That was 8 to 10% a year. So for a couple of decades, China, from a very small starting point, has been essentially doubling their space budget every 5 or 6 years. That buys you a lot of innovation. And China are planning a space station, a moon base, and a Mars base within the next decade or so, and they can probably do it. So it's like an object in your rear view mirror that may be closer than it appears. So China is approaching the US from behind with a very young and dynamic workforce. The average age of a space program worker in China is 27, I read recently, and in NASA it's 57. So, and there's a lot of experience in NASA, not to be discounted, but there's young energy in China, and they're not just knocking off American and European designs, Chinese copying, so to speak. They're innovating in their own right, and their own heavy lift rocket has got some significant improvements to it in its original design. So that's the competitive landscape, the geopolitical landscape. The little edge to it, of course, is the concern over the militarization of space. NASA was founded deliberately as a civilian space agency. Eisenhower, and when NASA was founded in 1959, had the choice where NASA could have just been an arm in the military and done some space exploration on the side. And to his credit, he very clearly carved NASA out in its charter as a civilian space agency. And around that time, the Cold War, people were concerned about nuclear weapons in space. So NASA has been clear of that. With the Chinese, nobody's quite as comfortable because the Chinese space program is so intricately linked with the Chinese military that Americans and Europeans and other observers are not completely confident that space will not get militarized under the Chinese. It's not what we know is not reassuring, even though there's no evidence that they're putting nukes. If they were putting nukes in space, I think we would know about it. So the geopolitical aspect of the space race is at a very interesting stage right now with the resurgent efforts of the Chinese, with the threat or the specter of militarization of space, the fact that the legal environment is sort of unresolved on that, and anyway, who would enforce it? It's not like the UN is really going to enforce nukes in space. They don't have the ability to do that. So that's sort of where we are right now, and the next 10 years are going to be very interesting.
All right, the next question is from Stephen via email. In your lectures, you talk about the wobble method as a way of detecting exoplanets. This sounds great if there's a single planet orbiting the star, but what I don't understand is how this method can work when you have multiple planets orbiting their parent star. Wouldn't each individual planet cause the parent star to wobble on its own?
Yes, exactly. So good question, and the answer is yes, it does. So if you have a multiple planet system, each planet adds linearly. Essentially, it's if you want to think about it, think about harmonics. Just think about a musical analogy. The wobble, when you measure you could always measure the wobble if you had sufficient technology, which we really don't right now, as a literal wobble in the sky. Just look for a star that is oscillating side to side with a period equal to the orbital period of the planet. We don't have the technology to do that. So the way the wobble is measured now is by a periodic Doppler shift of the star. That's the wobble of the star to and fro with the same orbital time as the planet. And that orbital and that signature, that wobble as a Doppler shift, is a sinusoid. And so you can think of it as a tone where the frequency, if you like, is the period of the orbit. And so if you have multiple planet systems, it just adds another overtone or a tone. So if you had a star with a exo-Jupiter and then an exo-Neptune and an exo-Venus and an exo-Mars or whatever planet you want, each of those planets in the system would be causing its own component of wobble and they would all add together, just as if you had a fundamental tone caused by the big massive planet and then some higher tones caused by the smaller planets on closer in, more rapid orbits. And so when people analyze the data, they pretty much do that. They do a Fourier, technically it's a Fourier analysis, where you can simultaneously look for multiple sinusoidal or periodic signatures in your data. Or you can look for the strongest signal and then model it, subtract it out, and look at what's left, and then look for the next strongest signal, model it, subtract it out, and look what's left until you're into the noise and the dirt. So those are the methods that people use. And it's actually nice because the signature of a planet orbit is such a simple signature, the sinusoid for a circular orbit, and it's just a modified sinusoid if it's elliptical. You can really look for multiple planets fairly easily. And this has been done now for 20 years, pretty much as long as exoplanets have been discovered. People have been looking for and finding multiple planet systems.
All right, so the next question is about gravitational waves from someone via email. There have been some rumors of gravitational waves that they've been found from the newly upgraded LIGO. What do you know about this announcement, and is it true?
I think not yet. I've heard some rumors too. It will be front page New York Times and all media outlet headline if LIGO finds a real gravity wave signature, and it hasn't happened yet. We'd all know about it. So we're just hearing rumors so far. LIGO is coming back into its science phase where it would expect to have the sensitivity to detect gravity waves. And there will be, of course, enormous disappointment if it finds nothing. Essentially, that will also mean the gravity theory is wrong, which will make theorists happy, but the observers will not be happy. There's nothing to look at. So no, I don't think gravity waves have been detected because we'd all know about it. There may be something bubbling behind the scenes. Also remember that for the first true detection of gravity waves by a new instrument like LIGO, they are going to be very conservative. Just use the analogy of CERN and the Higgs particle. The Higgs was first seen, there were hints of the Higgs data, I think in 2011, and they took almost 2 years worth of data through 2012 and 2013 before they really went forward with their claim and their result and their press release. So people are going to be very conservative and cautious with LIGO. They're not going to just leap out the first time they see a hint of a signal. Meanwhile, I'll mention that the existence of gravity waves, while not affirmed by LIGO, seeing them directly, has been inferred by binary pulsars, by the in-spiral rate of binary pulsars, where when you use conservation of energy argument, you deduce, because of the way the pulsars are moving towards each other and spiraling in towards each other, that energy has been lost from the system in the form of unobserved gravity waves. But the calculation predicts just the amount of gravity waves that general relativity would have said there should have been. That inference and that indirect observation of gravity waves was done several decades ago and led to a Nobel Prize in physics for Hulse-Taylor. So there's already been a Nobel Prize for gravity waves indirectly detected a few decades ago. The first real detection of gravity waves will almost certainly generate another Nobel Prize. And I think that's our time for this week. Now that we're in the new year, we'll be trying to do this every couple of weeks, and I look forward to talking with you in a week or so. Goodbye.